Anyway, yeah, so I will talk about geophysical inversion, and I basically working on two kinds of geophysical inversion and potential field inversion. So this gravity and magnetic data, and that's what I will talk about today, but also working on electromagnetic and electric data, the ERT and IP. I won't talk about this today because I believe that you guys are more interested in these potential field, large-scale potential field inversions. I picked this as a topic. So what I will talk in today is this is also an outline of what I will talk about. Is so we will talk about potential field inversion, and I will particularly talk about some techniques we have developed using finite elements to do that. We'll also talk about the esys-escript package, which is a project which I'm running for almost 20 years now with a lot of funding from Auscope. And so we'll talk about a little bit of what that is about, and because that's basically the framework we use to implement this inversion. I will also talk a little bit about joint inversion, basically looking at these data sets, gravity and magnetic at the same time in a single inversion. And if I have time, I will talk about not adaptive but adaptive measure refinements, which is sort of the hot topic for us at the moment. Yeah, so the problem we're looking at, is actually some work I did with Andrea Cott and from the UQ and Alan Acton from University of Western Australia. So Alan gave us a data set here from Kalgoorlie, in particular is working on for many years now. And we got some magnetic and gravity data for this region, and they're about 1 million data points each. And that's something you could would be difficult to do with conventional inversion techniques. So we looked at that, and there's a little bit of history in this, which I will come back to later. But we try to develop a very highly optimized and parallelizable implementation for inverting these, in the first instance, individual data sets. So just, I assume everybody knows what inversion is, but I just so be sure that we're all on the same page. So what I call geophysical inversion is basically from turning a 2D data set into a 3D data set, or 1D data set into a 3D data set. If you want to a bit more tackle a bit more challenging problem, but mainly what I have in mind here is 2D data collected on the surface or near the surface. You then need a physical model that basically describes you how any representation of your target, in this case it would be density and susceptibility, gives you an observation. Typically this would be in our case, it would be a gravity anomaly and a magnetic field anomaly. And so the task is basically solving to invert and find out to recover what the susceptibility and the density in that model was from some anomaly data. Yeah, so you can express that in terms of an optimization problem. So a little bit of math here. So basically, we try to find a density distribution here that minimizes some cost function. And obviously, what we want to do, we want to match some data. And so this cost function is composed of two parts, and a misfit part, and here, which measures the distance between a gravity prediction from a given density distribution to some data. And this process from density to gravity field is what we normally call a forward model. And in that terms of that inversion, it would be called, is actually constraint, because it constrains the gravity with the density. This problem, if you ignore this part here a little bit for a second, so this problem itself doesn't have a unique answer, unfortunately. So you need to add some regularization into this. And and which is typically, I will come back to this in 2 slides, but we typically can use the gradient of the density and try to somehow minimize that. And that is added to the misfit with some mating factor, which is called the regularization parameter, which is a bit of a dark art on choose. Now the misfit is, well, this is some sort of formal description of this, expression of this. So we have some gravity data, gravity prediction here, and some data. Normally we use some sort of Euclidean distance here with some weighting factor in front of that, which some sort of can reflect errors if you want. Also locality where you know the data, where we have a positive number and it has 0 where you don't know data. And this, as I said, this gravity prediction here is coming out of our density field. We have guessed it will be updated in the inversion process. So for each update, we calculate a new gravity field. That is done by solving the differential equation, this one down here, for the gravity potential. And from that gravity potential, we can calculate the gradient and then the gravity field, and then we can plug this into this here to get the misfit. Okay, so the task of this is basically make this misfit as small as we possibly can. But keep in mind that so each evaluation requires the solution of a differential equation. For the regularization, so this is what we use in this project, is basically the gradient of the density, the normal gradient of density square. And so basically what you're trying to do is to make the solution smooth, density smooth. And the degree of smoothness you get depends on the value of this factor mu. And that is an example here from a data set from Western Queensland with some inversion applied for different values of the regularization parameter. And as you can see, when you're for larger mu's here, you get a smoother density. Yeah, that comes at the cost of a lower misfit, of course. No, this part here has a better misfit here. But as you increase the mu, you get a smoother answer, but a larger misfit, no? Because you'll not be able to solve the to match the data very well. So there's, as I said, there is this art of how we actually choose the mu. I don't want to talk about this as a problem in itself a little bit. And you have done this, if you have done these kind of things before, then maybe you're familiar with this. Okay, what we use to solve that problem is the finite element method. And basically what the finite element method, that idea of the finite element method is to basically take the domain and cut it into little tetrahedrons in 3D or triangles in 2D. So this is an example here from a volcano. It's actually St. Helens volcano in the US, and we did some project we did or still doing with some people in France, where we're trying to map out the lava underneath the volcano from the electric surveys. So you can see the little dots here, density of the mesh where we have where the electrodes are positioned. And yeah, so in each of these tetrahedrons, the solutions are approximated by a linear function, and then these linear functions are stick together, so they're getting continuous. Okay. So basically, so it's a continuous piecewise linear approximation of the solution, and we apply that to the potential as well as to the density. And this is where things are a bit different what conventional inversion do, because they normally take a rectangular subdivision of the domain and may solve the forward problem with the finite mesh. That some people do that, but typically you still use a rectangular representation of the physical properties. So this is what we're doing here is different. We're using also finite element unstructured mesh for the approximation of the density. And so this is solved for the discrete problem. You can solve with iteratively or with this like a conjugate gradient method. And I'll come back to this later, to this discussing this a little bit more details what the issue here, but important, we're using a multi-grid solver, so we're not just using one unstructured grid, we actually use a hierarchy of meshes to do that. That is actually very important. I come back to this later. And you also we apply the domain decomposition. So this mesh is, I will come back to this later again, say a few more words about this, but basically the domain is cut into pieces and then distributed across different compute nodes in the cluster. So the fine element method, this is, as I said, is a little bit unusual to do this in this context, or actually very unusual to do this in this context. In electric method, it's a bit more common, but in tangential field, it's actually not. And there are some reasons for this, but there is also a reason why that isn't a good approach. Okay, so the solution it's actually a problem. If you look at this from a mathematical point of view, it's a quadratic programming problem, and that's why the inversion problem is a quadratic programming problem. So you can actually solve that also with the PCG method, but now that's one level up. So this is not solving the fourth problem, it's actually solving the inversion problem with the conjugate gradient method, which is an iterative method. So you improve your density in each iteration step, and there's some orthogonalization of the difference basically between the previous density and the new density against the previous increment. So you're trying to move orthogonal, your improvements try to be orthogonal to the previous improvement. So you really work very efficiently moving forward. That's some sort of the idea of the conjugate gradient. One of the big differences what we're doing, normally if you run conjugate gradient method, and some people do that in the inversion context as well, then using, if you have some quantity x, let's say you want to do the norm of that or sum it up over the grid, you normally just sum it up, okay, over all cells. The problem with this is if you have if I come back to show you this again, so if you look at the mesh like this, you can see that there are some parts of the domain where you have a lot of elements, some are not so filled with elements. So if you add this all up, you get the parts where we have a lot of elements get overemphasized in the summation process, and I have to say this is unfortunately wrong. So what you can do, you can weight this contributions by the volume. So this should not be, there's wrong here, so there should be no one here. So you can weight it by the volume to counteract the fact that in some parts you have a lot of elements and then some you not have so many. And basically what that means, you replace your sum by an integral. Only that's basically the same thing. That's basically what we're doing. So instead of using the conventional some sort of summing up over elements, what people call L2 method, little L2 method, L2 norm, we're using an integral norm. And is mainly because we want to address that problem of the unstructured mesh, but it has also some side effects which are a bit more deeply in the numerics, which I don't want to talk about so much here. And then, as I said, we apply a preconditioner, and what we do with this, basically, we use the regularization term and discretize that in fine elements, and then basically accelerate the convergence by solving in each step, correcting the step, or basically smoothing the search direction in each step, additionally to what we do for the density. And that actually, as it turned out, and you can theoretically prove that had a huge impact on convergence, and I will show you this later on. That is actually, you can achieve some very nice effects, which is called computational scalability when you do this. Again, I come back to this in a minute. Now, the thing is, when you do this, you have to, as I said, you have to solve the forward problem in each iteration step. Okay? You also need to solve the preconditioner step, which is basically the inverting the regularization term in the plus function, or the Hessian of the second derivative of this term in each step. And that's basically inverting the Laplace operator in each step for the preconditioning. And also, as it turned out, and that's something which is not so obvious when we need to understand a little bit better what's happening, we also need what's called a joint problem, which basically does the opposite from predicting the result for density on the observation point. It actually does the opposite. It distributes the misfit back to the density space. So we solve in each iteration step, we need to solve 3 differential equations. Okay. We have done this for the project here with Alan Atkin from UWA. So we have done an implementation of this, what I've just briefly outlined in esys-escript. using Python. And again, I will come back to this escript and what it does and how it works in a second. So the domain was 300 by 500 by 400 kilometers. And we used an unstructured mesh with 60 million elements to do this. So this is how the domain roughly looked like. So there is this inner core here, which is some sort of region of interest where you might apply depth weighting and all these kind of things. And that basically is chosen to actually be able to hold all the data in here. So this region here is as big as the data set here. We use a very fine mesh in here, which is basically determined by the resolution of the data. And then we're putting a buffering region around that. And there we're using a coarser mesh, which saves a lot of compute time, obviously. So this is like, this would be this mesh here. So this is the surface of the Earth in a sense, and the mesh, you see, looks like that. So we have a relatively coarse mesh on the side here. In the region of interest, and that's where the data are given, is much finer. So if you think about this, you would apply a rectangular grid with the same resolution for the whole domain. That would be quite a fine mesh and quite a big mesh, and definitely much bigger than 60 million cells. And you can play this even more. You could actually play a little bit with the gradient of the gradient of gravity to make your mesh actually more locally refined. We actually have done this for a point data set, or I'll come back to this in a second, where we're using local refinements, even in this core region. Okay, so this is some results on that inversion, and I cannot comment on this because I'm not a geologist, but Alan was very excited about these results. And if you are familiar with the region, you might see something I don't see, but as I'm more interested in the methods, not so much in the results. So if you're interested in how in this method I talked about, I refer you to this paper here that just came out, which with Andrea Kott and Alan Atkin, which basically described in more details what I was just talking about. The whole work get actually back to some work we did in 2015 I did with Alan in 2015, where we inverted the entire Australian continent. And we didn't use this PCG method, but we used BFGS method. So it's actually a nonlinear one optimization problem. And so basically what we have now is one which is far more efficient. I think you could probably solve that problem, which we did on, I think, 4,000 cores on the POSI supercomputer. I guess you can get this down now to a tenth of that resources to basically use the same problem with that far more advanced or highly more optimized solution scheme. I briefly said already that we have pushed it a bit further by basically using point data, right? So instead of most of these data set you get for gravity anomalies are actually point data on surface, and people apply interpolation to this data in some form. And so the idea was to take this actually out and do this interpolation basically at the point of inversion. So that basically you need to now invert not a map, but point sources, and that creates some mathematical problem. This paper, if you're interested in this, actually shows the method how you can do that. And you need actually higher order smoothing, so you need actually second order differential operators to which create some problems for the final method, but we have some sort of address that in that paper. Okay, I want to say a few words about escript. As said, that is a software we use to implement all these in all these three papers. They're all based on escript. So this is a method, is a software package or a module in Python where you can solve differential equations like these ones here. So the second order partial differential equations, also some boundary conditions, which is not shown here. And you can basically solve this on any with unstructured structures and unstructured meshes. And what you have to do, you write a little Python script which does a job for you. I will discuss that in a minute. I will give you an example of one of these scripts. And Basically, you can run this on your desktop, but you can also run with hardly any change this thing on a supercomputer. So this script I showed you with, we discussed with not the script, the method I'm always discussing before is basically developed on the desktop computer, and then we scaled this up by running it across a cluster. And if you basically don't have to change the script that much to achieve that. So this is sort of another view on these things. So it's the escript module is basically a module for Python to solve differential equations, as I said, and it's originally designed actually for rapid prototyping. And so you actually can do things very quickly, but not necessarily in the most efficient way. But it's interesting that actually in some, like for the gravity case, we can easily beat even C++ implementation because the highly intensive compute work is actually in C++. So there's only a small part of the code which is sitting in C++. In Python, most of the work is actually done in C++. So actually, the scripts you have is actually providing quite efficient implementation. It's very easy to use. So you don't really have to be a Python, so let's say, not have to be a C++ programmer to do this. And as I said, it's some sort of new supercomputer for the masses because you don't really have to do much work to get your program that you have developed on your desktop onto a massive parallel system like on this Magnum. We have done actually this code with Alan for the gravity inversion of the Australian continent. We have scaled this up to the entire POSI computer, which I think at that time was something like the first system viable at that time was, I think about 40,000 cores or something. So we scaled it up. We had a bit of problems to get the data out, but we were able to make it run and get an answer. But as I said, we couldn't do any visualization of the results. So here's some more info. So the project is actually started in 2003. So it's almost 18 years old project. And it's still funded from OSCOPE. And so it's funded till mid next year, hopefully till mid 2023. So then we'll then run for 20 years. It's an open source project on an Apache license. And if you're interested, you can get your source code here. We're currently at version 5.8. So this one is, as I said, source code, but there's also some binaries available for Anaconda, and you can install it for Linux and Windows. I'm not sure whether we have an Apple version. I don't think we have at the moment. And there's also, you can also get this through Debian package manager. So, but there are always a bit few versions behind. Normally, I think currently it's 5.6, correct? So, so I see it was. Hold on. So this is some applications we have looked over the years. So one of the original implementations back in 2003 that were actually metal convection. So this is an example here on 2D. But there's also example of porous media flow. This is this example here, which is talking about convection cells, forming convection cells in a reservoir, water reservoir due to temperature gradients. Geomechanics. This is some damage modeling here for rock samples. This was some work I did recently with Louis Kettle from Swinburne. There's also some, this is an example of seismic wave propagation on unstructured grids. That is a mesh of about 1 million cells, and with adaptive meshing to optimize the compute time. This is an example here on porous. This is what's this one again? This is erosion fronts in porous media. So this is when water is flowing through a porous media, that fine grain is transported out, and you get some sort of increased connectivity, which actually has an instability, and it forms some sort of fingering effects. You might have seen this on banks on rivers. This one down here is seismoelectric. So this is a coupling of a wave propagation and an electric response. So, so this is actually combining spectral element methods with classical finite element methods. And so this is two physical, so combining two possible physics together. All this is written in Python using the standard esys-escript library as a backend. So I briefly want to show you how it works. So just to give you an idea. So there is a general template for a second order differential equation, which basically looks like this. And basically what you need to do is you create yourself a class that basically gives you access to a PDE in this form, and then you have to say what the coefficients are, and then you can get the solution. That's how it is. So that's basically 3 statements in Python. It's not quite that simple, but that's basically the idea. And I'll give you a very small example just to illustrate how that works. So this is a temperature diffusion problem. I would love to talk about inversion, but the codes in inversion tend to be very a bit more complicated. So I'm stick to this very simple example. So there's a temperature diffusion problem here, rho Cp, and that's the temperature, time derivative of temperature plus the gradient or divergency of some diffusivity times gradient of temperature and some source term. So what we have in mind is a geometry like this, or we have a source in here. I don't implement it this way because the code becomes a little bit more complicated like this. But if you do this, I just want to show you the idea. But basically what we have in mind is a setup like this, where you have this heat source here, and that would create some temperature profile based on some top temperature maybe, and some flux from the bottom that you could mix in if you want. I don't do this in this example, but you could. So what you do apply, in this case, a backward for Euler method. So your time derivative here of temperature is approximately the difference of two temperatures on two time step n and n minus 1 divided by a time step, and you put this back into this equation here, and you're ending up with an equation like this here, where on the left-hand side you basically have it's divergency k times gradient Tn plus rho Cp over the time stepping times Tn minus 1, and then the source term, and then you have rho Cp over dt times T from the last temperature from the last time step. And if you compare this with this template, you can see that this K here is basically the A, rho Cp becomes D, and the right-hand side here is called Q plus rho Cp over dt times Tn minus 1 as Y. And if you use that, you can write a little script here. So we start, what you need to first start is you need to set up a domain. Here we're using a 40 by 20 grid on a 10 kilometers by 10 kilometer domain here. We create, as I said, a linear PDE object in a sense, if you're familiar with object-oriented programming. And then we set the values here for the A for the connectivity and D for rho Cp over dt. And this is the initial temperature here, which assumes 20 degrees. And then you can write your program here to iterate over this time stepping. So in each time step, we need to just update the left-hand side, the right-hand side Y, which is Q, which is the source, plus rho Cp over dt, and time the temperature from the last time step. And then we get the new temperature. Then we get the new temperature. And we can save this here into a visualization file and calculate the flux as you go. And then we go to the next time step, and you can just iterate over this till you reach the given number of times. So this is, you see, there's a high level of abstraction. There's no talking about finite elements. There's no talking about arrays. This is all in the PDE coefficients are all abstract objects, which you don't really have to worry about what they actually are. So one thing which is important here is this point is just look at this thing here. So Q plus rho Cp over dt times T. If you go back and you see Q in this case is actually a constant, and rho Cp is a constant here, and dt is a constant, but temperature T is a solution of the previous PDE. And so what happens behind the scene here, which you don't see, it's automatically because there is an awareness of the context of data objects, that you need an interpolation because the Y typically is stored on element centers. Watchdog points, automatically there's interpolation happening because the system knows that at that point you need to have data on the integration points. But these ones are given on finite element nodes, so there is interpolation happening, which is automatically done for you. You can, so you can send this script. Actually, you can run that on a cluster as well. with practically with the same run, no change on if you want 10,000 courses. And what happens then behind the scene is also the distribution of data, communication, all this kind of stuff. That's all hidden from the meter. So it would be a result with Visit, or you can use ParaView or Matplotlib if you want. That result is not matching what's in the script. That will be a more trivial example. Yeah, so as I said, there's looking under the hood. So there's a Python part, which is this some sort of orange layer here, which is the data object. So this is like a solution of a PDE, which is stored in all the elements, nodes. There's a domain class, which basically is matched down on the C++ level to a mesh. Then we have a PDE, which basically is corresponding to a sparse matrix solver. And the data object, which is, again, basically managing how you store like the temperature on each node of the final element map. This is nothing else in the bottom line, like an array handling. So it's a bit more complicated than this, but that's basically the idea. So there's its Python abstraction layer you're dealing with, as I showed you in the script, and there's this underlying C++ implementation, and that also links back then into MPI and OpenMP for the parallel. You can also link with third parties like the software like SciPy, Matplotlib, PYMC3 if you want to do some Markov chain Monte Carlo modeling. So there's through the NumPy stream in Python, you can connect with these packages as well. Okay, the architecture we have in mind for this, I'm running out of time a little bit here. The architecture we have in mind is basically this would be what you see in the Magnus HPC facility in Western Australia. So we have basically nodes here that have, in this case, 4 CPUs, and each of them, 4 CPUs or let's say 4 cores sharing memory, but this node will not see the memory of all the other nodes. You have to do explicitly do message passing. You have to send a message from data from one node to another if you want to use data from the other node. No? So this you need a good understanding of what your memory access is and synchronization and all this kind of thing. So it's this process from getting data from here to here is a labor, is compute programming work. And that's actually not needed to do because the scripts in part each script give you an abstraction from that. There's also a shared memory component in this, so that because all these 4 cores here in this case share the same memory. That's basically to threading and object P. So that comes on top of the parallelization across the node. So you have a hybrid style of parallelization. Again, it's your script. The script I show you would run on that with this platform with no change. Okay, a few words about computational scalability. So the question is, can you actually run these scripts? Or what resources are needed to run a script on a cluster in this architecture I just showed you? So one of the things is memory requirement. So if you think about, you would load the whole mesh on one node, you run into a limit, right? Because at one point your memory would need a lot of memory to store all these element nodes and all the data and everything with it. So eventually you would run out of memory. So this script doesn't do that. So it's always, so you apply domain decomposition, like in this picture here. So the mesh is cut into pieces and each of the nodes get a piece of the domain. And at no point in the calculation, the entire mesh is stored on one node. Okay, so that means the memory requirement per node is scalable in the sense you increase your mesh size. The storage you need, the memory you need per node is not increased. So there's technically from a memory point of view, is no limitation. That's what we call scalability. There's of course a problem load balance. In EScript, that's totally done by data volume. So how many elements and how many nodes? That's not necessarily a good way to do this, but because it's a dynamic script, we don't know exactly what's going to happen. That's the only way to basically do this. Oops, the problems come up. Sorry. Problem is communication costs, because as I said, you need to hand over data between different nodes. And of course, that slows down potentially the calculation time. And And so there's an issue that you need to optimize that as well. For instance, that means that portion of the domain that are close together also should be on nodes, computational nodes that are close together. Right, so that's one of those things. Also need the volume, the contact volume, so the volume of data you need to exchange between the different subdomains need to be minimized. So this is all things that escript implements. The core problem actually is compute time. Okay, so what we want to have is that if you basically like you double the number of elements and you double the number of cores, then you want to have the same time because you're solving a problem with double size on the double compute resources. That's what we call computational scalability, and that's actually a problem. This is something which is extremely difficult to achieve because like when you do an iterative solver or even the direct solver, it's worse. The compute time is actually typically growing quadratically with the number of unknowns, or if you're lucky, log n. That's a good thing. But most of the time it's n squared or n to the power 1 over 3, some of these. So you don't really get that what we call computational scalability easily. It's very difficult. Okay. And I'll show you this here now for the IPCG that we actually very close to that. So this is the inversion of the gravity data I showed you initially. And if you look at this number here, so this is the cells, the number of vertices, you know. And you can see we start that number here. This is the relative size given. So we're starting with this 42,000 30,000 node mesh here. And this here is the relative scale. So this mesh here is about 230 times bigger than the first mesh. And now this here is the number of iteration steps you need to solve the gravity forward problem. Okay, you can see this number is slowly increasing here. It's not too dramatic, but it is increasing, and that's thanks to the multigrid method. Okay. We're using when solving the forward problem. The inversion here, you can see the number of iteration steps here is constant. It doesn't change. Now, this is very important. So we not with bigger meshes, we not need to have more inversion steps. That's a very cool thing. And if you look at compute time, and again here we use the 51, the first row here as a reference, and we scale all the times we have here relative to the first one. It's not entirely true. Because 1 point, I think there's another reference. It doesn't matter. Important is that this number is, if you look at this, this is increasing in the same time. It's increasing at the same time at the same rate as the time increases. So we have a linear relationship between compute time and problem size, almost linear. Yeah, that's what when I talk about computational algorithmic scalability, that's what I mean. If you use a classical inversion algorithm, you won't have that. That will probably be quadratic. Okay? So that's something which we can achieve because we're using multigrid. The other thing is that's more an implementation issue. So how do we work with MPI? So we solved the 60 million cell problem, and we solved that with an increasing number of nodes or cores, right? And we look at the efficiency, that's actually the time we used on P nodes divided by P times the time for the node 1. And what we're expecting in this is 1. And you can see actually that we actually better than 1 here. Okay. And so that actually means that relatively speaking, this one is faster than this one. That is because of cache effects, because your problem you have per node is becoming smaller, and then you have better memory use. You have less cache misses. This is why these ones here are actually faster than this one. Okay, so in terms of computational scalability, we're very cool here with this inversion. All right, first we have basically we can scale up with processes. The more processes we use, the faster it gets. There's a limit to that because combination cost comes in. And then we have also the problem of what the other showed you, that the number of iterations that actually is the compute time over the iteration, over the inversion is actually also scaling with the number of elements. So we have this computational scalability on that one. Okay. Sure. I can quickly talk about joint inversion then. So coming back to the original the original problem where we have gravity and magnetic data. So it's a closely computational performance discussion, and come back to geophysics here. So what we want to do, this is some sort of stepping this up, not looking at these separately, but looking at them at the same time in a single inversion. Okay, and that's some work I did. I did 2 years ago. And so the idea is that you actually assume a functional relationship between density and susceptibility. Okay. Now, on a lab scale, that is possible. Like if you to basically go and measure, take samples and correlate them. And this is some work I'm doing with people in France, where they actually did that for a region of volcano. And so we have actually a good understanding of how in this time, it's actually the chargeability and the electric conductivity, how they are connected to a functional relationship. Actually, it doesn't turn out they're related to temperature, but then that means you can eliminate the temperature and you have a relationship between chargeability and conductivity. Now, in a scale of 200 kilometers, 400 kilometers, this is probably not realistic. And so you say, well, that's not feasible. But what you can do, you can take the gradient of this, and I'll do this in the next step here. So if you take the gradient of this relationship, you can see that gradient of what you get is gradient of M1, so the density is f dash, that's the derivative of this function with respect to susceptibility, is times a gradient of the susceptibility. And this is a scalar. That means these two vectors, the gradient of the susceptibility and the gradient of the density, need to point in the same direction. Yeah. And so if you have this little picture here, so if you think of being that the contour of the susceptibility, and that's the contour, the blue one is the contour of the density, and you look at the normals to that contour, then the angle between these two here, alpha, I call this alpha here, has to be 0. Yeah. So that's the conclusion from the fact that there is a functional relationship between density and susceptibility. And one way to actually express this angle alpha here, which is the sine of alpha, is taking the cross product of the gradients. This is what this is called as a cross gradient correlation. And what you want to have is that this cross gradient is actually 0. So if it's 0, then the two gradients point in the same direction. That means there is enforcing that is because we have a functional relation between them. Okay. But keep in mind, we don't need to know what the exact functional function is. Yeah? We just know that there is a scalar between the two gradients, and that fact we need. So we don't know exactly. We don't know the function itself. We don't need to know. Okay, so what we can do now, sorry, a bit of math here. So we can basically now go and take the part of the density of the inversion. So this is misfit of gravity observations plus regularization for the density. We do the same for magnetic. So misfit in magnetic plus regularization of the susceptibility. And of course, there are four problems involved here because we need to match the, the gravity with the density and the, magnetic field with the susceptibility. So each of them have two constraints come into play. And then what we also do, we just take this cross gradient term here. I'll get this one here, and we add that to the cost function with some penalty factor. Okay. And so when you minimize that, we hope that, or the idea is that then this cross gradient term will be small, not necessarily 0, but small. Okay. Almost 0. That means the angle is almost 0. Keep in mind that cross gradient is proportional to the sine of the angle. Now, it's also proportional to the gradient of density and gradient of susceptibility. And basically, to balance this a little bit better, one can introduce the scaling factor. Okay, so this is very technical. And basically, this paper I referred to before is looking at this in particular, what is a good strategy to balance that matter. Okay. So So this is very technical, and there are reasons why that is a good choice, but we don't have to talk about this today. So basically what we now solve is, instead of one, so only this part here, you need to in each step to solve two forward problems, basically, now for density, susceptibility, and you also need to do the adjoint problem, to the backward distribution of errors for gravity and errors for magnetic field back to the density and the susceptibility. And also we do, keep in mind we have now two unknowns, no? And then we have also two regularization steps. And then there's this extra cross gradient term, which comes into the cost function, which is easy to calculate. Okay, so that is now not a quadratic programming anymore. So the classical PCG, which we did before, cannot be applied. So we need a Newton scheme here, and we're using the BFGS, which is a quasi-Newton scheme. Not so terribly important. Again, it's two unknowns, M1 and M2. Again, we're using this idea of an integral version of the BCGF with BFGS, which is a bit unusual because normally you go back, like I said before, we normally sum up over cells, but we do here, again, weighting with cell volume, so basically using integrals. And we apply a precondition in this case only, again, only the regularization terms for the susceptibility and for the density. So in ignoring, which you could do, I've tried that, you could also calculate into the precondition with the cross gradient term, because you can calculate the Hessian, but that is too expensive and does not improve convergence. Again, we have all this implemented in esys-escript and with finite element, and you can run this on a parallel solve, on a parallel cluster, and that is an example from Central Queensland. So this is this is black and white or gray. So there's some anomaly data from here from Queensland and magnetic, for gravity and for magnetic. The inversion was 30 million cells on 200 cores. So that would be 10 compute nodes and 20 cores per node. Now, what I will show you in a second is the result from this at a given depth. And I plot also basically checking whether the two gradients are pointing in the same direction. I calculate this measure of correlation here, which is basically the dot product of the two gradients of density and susceptibility, and I scale that by the length. And so this number is between -1 and 1. It's basically the cosine of alpha. So if that value is 0, right, or small, that means the values are orthogonal, the vectors are orthogonal. If it's 1 or -1, then they're pointing in the same direction. Right? So this is we can plot that, and it's a nice indicator whether the we actually need, in the version result, we actually need the cross gradient constraint, because we're not explicitly constrained, we just have that as a penalty. So this is a result here. So and the reason why I show you this is because there is some very cool effect you can see here. So this is the color is density, and that's density susceptibility. The black area here is the one where the value for m squared, so I'm using the m, the square of m, if that value is less than 0.97. So that means in this region where you see black, the correlation between the two vectors are not necessarily covariant. Okay, they point in different directions. They're not in the same direction. And you can see what's interesting is what you can actually use this inversion for is identifying interfaces between geological units. Because what that means, that in this region here, you know, this assumption, because it's assumed that the function f, which describes the relationship between density and susceptibility, is not depending on x, not on the spatial coordinate. But if you, so that means within, this assumption is correct within this region here, but in this region here, but it's not correct when you cross that interface here where we see this large m, right? So that is an indicator that, like in this east flank here, or western flank here, we have an interface between two geological units, because this correlation function between M1 and M2, or density susceptibility, is changing while you're crossing that line, right? Again, this is the point where the correlation breaks. Okay. Yeah. Good. So you can see that what I'm trying to show you is that how this joint inversion can be used actually to identify geological units. It would be nice to automate this process of basically trying to connect all these dots. I haven't really looked at that, and I think it's a bit complicated because if you look at this region up here, for instance, it's not that often not that clear. So here, obviously, there's a lot of action, and it's not a clear picture what the interface actually look like. But here in some region here, if you look here, it's very clear and very smooth. And so I think automating this process might be a little bit complicated. Okay, I want to talk about mesh adaptability, but I don't have any time, so I'll jump over this a little bit here. And come to my last slide here, which is this one here. So one thing I want to get across to you is that you appreciate a finite element-based inversion, right? So rather than what's conventionally done, where people basically using a rectangular grid, and also not appreciate the fact that you could approximately, you can actually calculate all the regularization terms in terms of a finite element approximation. Most people using what's called a Raffnet matrix, which is some sort of funny construct, and does some interpretation in a rectangular context, but rectangular grid context. But if you go and use finite elements for this, it's a natural way of doing it. But as I said, there is also the advantage that we get a nice and very scalable code, as I'm trying to demonstrate. So we can achieve computational scalability. And again, king gradient is multi-grid, okay, for solving the forward problem, but also multi-grid to invert the regularization term. So for the preconditioning of the inversion problem, which is also a very important step. Which I wanted to talk about is something of the next big thing for us in this context is actually using mesh adaptivity. So what we want to do is at runtime, find out where actually we should have more elements in the mesh, because we suspect that or we can see that there's a large gradient in the density or in the gravity, and we might have to pull through, or we can reduce the error we do by putting more nodes in there. And that's something we would like to do at runtime, because in advance, obviously, it's not clear where we will have a large gradient and where we have to put more elements in. So something we have started already. So we have some prototypes for this, but it's not totally integrated into EarthByte yet. My few slides ahead wanted to talk about this a little bit and get some appreciation of how much compute time that actually can save you when you're a bit more clever on using this idea of runtime. Runtime optimization of the mesh in a sense, but again, this is something which hopefully comes next year in some of the, probably later in next year, we will have a first version in EarthByte. Thank you very much.